to one another. And so the Poisson equation, it defines the flow rate, and it turns out that the flow rate is dependent on several variables. The Poisson equation is pi, which is just a number, r to the fourth. That's the radius of our vessel. Let's say it's a pipe or blood vessel or whatever. It's the radius of it. Our change in pressure, as you know, anytime you have a fluid that has some viscosity, you need a difference in pressure in order to make it move, in order to continue it moving through the system, divided by 8, just constant, eta, that's the Greek letter eta, and L. So R, as said, is the radius. Delta P is the pressure differential, or the pressure difference. Eta is a measure of the viscosity. This is, as I said, it's a Greek letter ETA, the Greek letter eta. And then L is the length. So if I'm looking at a vessel here, R is this radius, L is the length of the vessel, and then if this is P1, the pressure at one end, and this is P2, the pressure at the other end, then delta P is equal to P2 minus P1. Just what is the difference in pressure between 2 points within that vessel? And then eta describes the viscosity. How thick is the substance within the vessel? So what happens to Q when you change these variables? Well, as you notice, Q is most dependent upon which of these variables. If you change which of these variables, what changes Q the most? Which variable, if you change it, will change Q the most? Well, let's take a look at the equation. I have pi r to the fourth delta P over 8 eta L. Let's say I increase the pressure. What does that do to Q? Say I double the pressure. I double the pressure differential. What is that going to do to the value for Q? It's going to double it, right? Because if I double one side, I have to double the other side. And similarly, if I double L, what's going to happen to Q? It's going to do what now? No, it's not going to double. So if I double L, yeah, very good. So if I double this, I'm going to get a factor of a half over here. What happens if I double R? Say I have R and then I make it twice as big. What happens to my flow rate? Keeping everything else the same. Does it double the flow rate, Q? Well, no, it's not going to decrease. If I double R right here, I know you're sort of thinking physically what would happen if I make that pipe bigger, but if I make the pipe bigger, I'm assuming that everything else remains the same. One, that the pipe remains full, and then I also still have the same pressure differential. Now, what you're thinking is that if I have a pipe and I make it bigger, then the pressure is going to go down. And that's true, right? In practice, that's true. But if I have a pipe and I think about all those things remaining the same, including the pressure differential, including the viscosity, everything else, what happens if I make the pipe twice as big? Think about the equation here. If I make R twice as big, what does that do to the right-hand side of the equation? How much bigger does the right-hand side of the equation get? Let's go back. It's going to go up. Let's go back. Early on, we looked at an equation like this. Y is equal to x squared. And I said that if we doubled one side of that equation, what would happen to the left-hand side? It wasn't double. It does what? It doesn't have, okay, not 2x. I'm going to get a factor of 4 over here. Because this variable is squared. When I double it, I get a factor of 4. Remember quadratic equation? That I have this dependence that's not linear, it's a quadratic dependence. So what's going to happen to Q if I double R. If I double R, what's going to happen to Q? Does it get bigger or smaller? A lot bigger, right? 2 to the 4th bigger. 2 times 2 times 2 times 2. So that's 4 times 2, 8 times 16 times bigger. So if I double the radius R, I'm going to get 16 times the flow rate going through that pipe. And again, don't think about it in a physical intuitive sense. Just look at the equation, because I'm assuming that as I make the pipe bigger, that it remains full of the fluid. Whereas normally if I made the pipe bigger, then it would just sort of fill the bottom of the pipe, right? Okay, so if delta P goes up, if it increases, then Q will increase by the same amount. But if R goes up, then Q will increase by a lot more, by a factor of R to the 4th. So if it's halved, it's a factor of 16. If it's doubled, Q increases by a factor of 16. If it's tripled, Q increases by a factor of 81. If it's quadrupled, it's 256 times the flow rate. So Q is greatly dependent upon the radius. You had a question like that, I think. Did you? No. Okay, well, it's an important question. That Q, the flow rate, is very much dependent upon the radius. All right. I feel like I'm missing something. Oh no, it comes up a little bit later. All right. So, applications to the human bodies. You need to have a basic understanding of the circulatory system and how some of these principles of fluid flow apply to the circulatory system, and then also some of the other fluid systems in the body, the digestive system. But mostly looking at the circulatory system. There are 2 parts to it. The systemic circuit. That takes blood to the body. Takes blood from the heart to the body. This is sort of what you think of when you think of the circulatory system, right? It goes from the heart, and then it goes out to all the different parts of the body. And then there's the pulmonary circuit. This is a much shorter system because it just goes from the heart to the lungs. It takes, I'm going to put used blood. That is blood that's been deplenished of its oxygen and whatever nutrients. It takes used blood to the lungs for replenishment. Right, so those are the 2 basic systems. You should be able to define them, or at least pick out the definition from a selection of choices. Now we'll consider this system to be closed. The book talked about what a closed system is. That means that nothing comes into the system and nothing goes out of the system. So because of that, or we talked about this earlier, that because of that, then the flow rate is constant. Remember the flow rate, that was Q was equal to delta V over delta T. That's our volume flow rate. That's how we describe the flow of fluids. And if you have a system that has nothing coming in and nothing going out, then this remains constant. Yeah, Kate? The pulmonary circuit takes blood from the lungs to the, or from the heart to the lungs. So it takes used blood to the lungs for replenishment. Goes from the heart to the lungs. I'm sorry, you got that? Okay, yeah, remember that this whole thing, this statement that we're saying, that this brought about which of our equations? let's do it as a clicker question. So we had several principles or equations. We had Pascal's principle. We had the Poiseuille. I think that's right. The Poiseuille equation. We had the equation of continuity. And we had the pressure, like pressure at a certain depth, the P equal rho GH. I think those were all the equations that we had. So this statement gives rise to which of these equations? The Pascal's principle, the Poiseuille equation, or we just looked at the continuity equation, or the pressure at a certain depth, that P equals rho GH. Yeah, this statement. Oh. The statement that a system is closed so that the flow rate is constant. That gives rise to which of these equations? Pascal's principle, Poiseuille equation, continuity equation, or that P equal rho GH. Remember, Pascal's principle said that if I had a pressure, the equation that came about from that was that P1 is equal to P2. If I apply a pressure to a container, that pressure is felt all the way throughout. All right, let's stop here in just a few seconds. Stop at 55. You get? Okay, no, the answer is C, y'all. Oh, come on. It's the continuity equation. Remember the continuity equation? We started out with this Q1 is equal to Q2, but then we said that this delta V over T is the same as area times some length over delta T. Remember we said that volume is an area times some length, and that this is the same as our velocity. So we had A1 V1 equals A2 V2. That is the equation of continuity, and it arises out of the fact that the flow rate is constant in a closed system. Yeah. Y'all don't remember that? Come on. All right. Now, since blood is viscous, it's not, like water, it's thick. The Poiseuille equation applies. And for viscous flow, you need a continual drop in pressure. That's why your heart has to continue pumping all the time, day in and day out, and it just gets tired sometimes. Just boom, it's all the time pumping, because you need this continual pressure differential in order to move this viscous blood from one point to another. And that's represented in the Poiseuille equation. That's where this, if we think about the Poiseuille equation, pi r to the 4th delta P over 8 eta L, that's this, that we have to have that pressure differential in order to have a flow rate. Okay? So I want you to know the order of blood flow and also the basic chambers of the heart. The order of blood flow after leaving the heart, it goes from the aorta. I have a picture, I'll show you this in just a minute. An aorta to the arteries, to the arterioles, which are like smaller arteries, to the capillaries. All right, and then returning back to the heart, that used blood will go through the venules, the veins, and then the vena cava. Look, and these go from big to small. So this is big. I don't know, probably fit your thumb in the aorta, or your maybe your index finger. Anybody ever seen an aorta before? Like a human aorta? Have you? Seriously? How big is it? Finger? About? What was it like? Was it cool? May I ask how you saw it? Is it a personal question? And they gave you a human heart? So there's an actual human heart? Was it like
It was like a nursing class.
was it flesh?
I don't know, I didn't touch it.
I just didn't think they'd give this thing to anybody. Do they? You just go out and buy a human heart? Can you?
We didn't get one at my nursing class. I'm jealous now.
I thought it was like that serious or something. Anyway, it's a big thing. And then you go down to arteries, and then the capillaries are tiny. We'll talk about the capillaries soon. And then returning, the venules are small. They're sort of like the equivalent of the arterioles. And then you come back to the vena cava, which is big. All right, so you have 4 chambers in the heart. The atrium and the ventricles. Atrium, as I said, is up top earlier. It's like the atrium in a hotel. And then the ventricles are down bottom. And so the atrium is up here. Those are your 2 chambers called the atria. And then the bottom chambers are the ventricles. And then it's like stage left, stage right. It's not left, right. It's stage left, stage right. So like this side is the right side, and this side is the left side. And this is the right ventricle. This is the left ventricle. Right. It's because like my heart, this is my left side of my heart, and this is my right side of my heart, right? That's how I remember it. So the atria is up top, like the atrium in a hotel, like the big windows in the hotel, and is that the atrium, the windows? You don't know what I'm talking about. Like that, I think that's what it is, the windows up in the ceiling. And then the ventricles are down bottom. Or if you want to think of it as alphabetical, A, V, but I always think of an atrium in a hotel. I don't think about the atrium that much. But when I do, I think of the atrium in a hotel. So blood flows out of the left ventricle through the aorta. It goes through the systemic circuit. And then it returns depleted to the right atrium. Then it goes to the right ventricle. Through the pulmonary artery. Pulmonary just means lungs, like a pulmonary doctor, that's a lung doctor. To the lungs, and then it returns to the left atrium through the pulmonary vein. Once you have just a basic understanding of how blood flows through the heart and how it goes through the different circuits, the systemic circuit and the pulmonary circuit.
Do you have a video?
Yes, I do have a video. I'll show it to you in just a second. This is a picture of the heart you have in your book, and it shows the different parts. So here's the right atrium and the left atrium. You get that used blood, which comes into the vena cava, goes into the right atrium, and then where does it go from there? The right ventricle. Right? Know what I said? Hold on, I get that wrong. I'm pretty sure that's right.
I think you just did it backwards.
Oh yeah, so it goes through it comes into the vena cava through the right ventricle, right atrium, right ventricle. So that's sort of the second paragraph of what I wrote. And then from there, it goes to the pulmonary artery, and then you got the lungs over here, right? And then it comes back through the pulmonary vein, and returns to the left atrium, and then it goes through the left ventricle to the aorta, and then it goes out to the body. So if you switch those paragraphs, that might help you see it a little better. But the paragraphs are not incorrect. All right. What's that? You can if you want. Doesn't really matter. You can keep them the way they are if you like. So there are 4 one-way valves in there, and the book does talk about those valves quite a bit, but I'm not going to test you on the valves. But you can see here that there are some valves. The tricuspid valve, and this is where the blood comes in, but it can't go back out again. So these valves will open up. I'll show you a video here. And then there's some other valves here and here. They keep blood from sort of, backwash, right? You do this is like when you're drinking a soda. Keep the soda from leaving your mouth and going into the bottle. This is kind of gross, right? Because that's where you get all the spit and stuff in your soda. You don't want that going on in your heart. That's why I have a video. It's really sort of more of an animation. Oh, we'll watch that soon. Let's try these questions. Yeah. Let's try this one on the left. Right here. While you're doing that, I'm going to run and grab something. So answer that question. I'll be right back. All right, so I'm going to stop here at 1 minute, just a couple more seconds. Okay, so what happens to the speed of the blood when you have something like this that's partially blocked? Well, remember, our continuity equation, A1V1 is equal to A2V2, that this is still going to hold. So that means that if my pressure here, my area decreases, that means that the speed has to increase, right? It's like in a water hose. When you put your finger over the end of the water hose, that the speed of the water coming out, because the flow rate must still remain the same, the speed will increase. So it does increase. A is the right answer. We'll see this again soon. Where does it come up? Yeah, we'll see it come up soon. We'll talk about it later. All right, consider the Poiseuille equation. What happens to the overall blood pressure as a blood vessel becomes partially blocked? So this is our Poiseuille equation. Pi r to the 4 times delta P divided by 8 eta L. What happens to the pressure, the blood pressure, the overall blood pressure, as the blood pressure becomes partially blocked? Just a few more seconds. I'll stop at 54. Okay, good. A is right. That's sort of what we think of, that when we have a blockage in our artery or a vein, that we're going to have a pressure increase. And that's what the Poiseuille equation says, that if R decreases, as it does here, then our pressure is going to go up. In fact, it's going to go up a lot. That if R decreases, say, we have this R to the 4th delta P. If R decreases by, say, a half, then that means that P has to increase by a factor of 16 in order to keep that flow rate the same. Now, we will also see a little bit later that I'm going to say the exact opposite of this. I'm going to say that the pressure in your artery doesn't increase, the pressure decreases. And so when I say that, don't freak out, because I'm talking about two different things. Here, when I'm talking about the pressure, I'm talking about the systemic pressure, the overall pressure that's required to force your blood through the entire system. So it's like the pressure that originates at the heart. But later, we're going to talk about arterial collapse, when an artery actually collapses, because that's what happens when you get an artery like this, that eventually it will collapse. And if you have a high pressure in here, that doesn't make any sense. Why do I have collapse if I have a high pressure? The pressure should keep that artery fully open. But that's not what happened. And we'll talk about why that is a little bit later. Just don't freak out when I say that when the speed increases, the pressure decreases, because we'll be talking about a different type of pressure. Here we're talking about the systemic pressure, the overall pressure in your circulatory system. What does the pulmonary circuit do? All right, let's stop at 25. Awesome. It takes blood from the heart to the lungs. So anytime you hear lungs, you just think pulmonary. What do they do with a chemist when he dies? You never thought about that, huh? What do you think they do with a chemist when he dies? They bury him. Okay, it takes blood from the heart to the lungs. And which of these is the rate of blood flow the greatest? Now remember, the aorta, which is part of the systemic circuit, it's the big thing. You stick your finger in there. Capillaries are really tiny. They're at the end of the systemic circuit, and then they turn around and coming back. Venules are a little bit bigger. They're sort of like, the arteries. Not the arteries. What are they like? The venules are like the arterioles. Excuse me. Thank you. Yes, let's play. All right, let's stop at 23. Yeah, very interesting. So you'd think that the aorta might have the largest rate of blood flow, right? Because it's so big. But then you might say, well, the capillaries, there's what of the capillaries? They're really small, but there are what? There's a lot of them. I don't know how many, thousands maybe? Millions of capillaries? Billions of capillaries. There's a lot of capillaries. You need a lot, right. But, well, what case? Well, we're not thinking about pressure here. We're thinking about the rate of blood flow. And in a closed system, rate of blood flow is equal to Q. In a closed system, if you don't have anything coming or going, which is effectively what we have in the circulatory system, it's going to be the same. So it's the same throughout the entire systemic circuit.
I was thinking there was this picture in the book where it showed like different rates, I guess, and the capillaries had the biggest one. So I guess that's what I was thinking of, because obviously not the same.
The biggest ones.
Yeah, it was like 900. I don't know.
Just make sure that we're on the same page.
Yeah, it's that one.
This one right here.
No, the other one. See how it says capillaries.
Yeah. So this has a speed. Talking about this picture, I'll show you a similar picture. And it shows you the speed of the blood through the capillaries is about 0.1 centimeters per second. But the speed through the aorta is 30 centimeters per second. Remember, speed is not flow rate. Speed is a velocity. It's a speed, a distance per time. But flow rate is volume per time. And so what's another important number in this figure on page 56 is the cross-sectional area. Because it has 3 centimeters squared for the aorta and 900 square centimeters for all the capillaries combined.
So I read it wrong.
Yes. Well, if you
Because I was thinking that was the speed.
No, that's the cross-sectional area. And so if you multiply the two, if you do 30 times 3, that's 90 cubic centimeters per second. And then 900 times 0.1, that's also 90 cubic centimeters per second. So you get the same volume flow rate in the capillaries as you do in the aorta. And the arterioles and the arteries and the vena cava and all the different parts of the systemic circuit, you get the same blood flow rate. So, as blood flows throughout the systemic circuit, experiences a continual drop in pressure. That's that delta P in the Poiseuille equation, that I have to have a difference in pressure from the beginning to the end in order to make that system flow if I have a viscous fluid. The highest pressure is, where do you think? Where do we have the highest pressure in the systemic circuit? Well, if we go back to look, at our order of blood flow, where do we have our highest pressure in our systemic circuit? Where do you reckon? Where are we going to have our highest pressure, and where will we have our lowest pressure? From the aorta to the arteries to the arterioles to the capillaries.
The aorta?
The aorta, right. That's just after it leaves the heart. The heart has just pumped that blood.
Yeah, I got this wrong.
Okay, yeah, it does have the biggest pressure, but still the same flow rate. The flow rate's always going to be the same. Biggest pressure, and then all the way down to the lowest pressure at the vena cava after it comes back. So we have this continual drop in pressure. Where? And am I on this page? Yes, okay. So the highest pressure is in the aorta, and then the lowest pressure is in the vena cava. All right. So Poiseuille's law says that the pressure must be higher for flow through longer systems. Right, Q is equal to pi r to the 4th delta P over 8 eta L. What we're talking about here is that if Q is going to be, if L is big, if L increases, then that means that my change in pressure increases too. That makes intuitive sense, that if I have a really long water hose, I'm going to need a higher pressure in order to push fluid through that water hose. And the same is true for our circuits, our systemic and our circulatory, our systemic and pulmonary circuit. For that reason, the pulmonary circuit is much shorter than the systemic circuit. Remember, pulmonary circuit takes it from the heart to the lungs. Not very far to go. It's a tiny little short thing, a little jaunt over to the lungs to pick up what it needs and then to come back. But the systemic circuit is a lot longer. You got to go down to the feet, up to the head. You got to go all up to the ends of the arms. So because that's pulmonary is so much shorter, the pressure there should be less, quite a bit less, because L is smaller. L is small for the pulmonary circuit.
So for someone who's like really, really tall, then their pressure has to be higher.
Right. So have different types of pressures, the systemic and the pulmonary. These are the systemic circuit, that pressure is about 80 to 120. It's like your blood pressure numbers. Millimeters of mercury. And remember, the millimeters of mercury, if I have a cylinder and I get this fluid that comes up inside of it and I measure that height, and that is measure of the pressure. All right? Y'all seen the little cylinder when you go to the hospital and they have the tube and you see the little cylinder of mercury rise up? That's what they're measuring. How high does that column of mercury go? And that's a measure of our pressure, and that pressure is equal to rho times G times H, which we've seen before. And that's how we measure atmospheric pressure too. The pulmonary circuit is 10 to 25 millimeters. Of mercury. So much lower pressure in the pulmonary circuit. Your blood pressure measurements, are these gauge or absolute measurements? Do you remember the difference between the two? When they take your blood pressure? Right, it'd be a gauge measurement, because you always have to include in sort of the atmospheric pressure. Remember the difference between those two, that our absolute pressure is equal to my gauge plus the atmosphere. Yeah. And then we have two numbers when we measure our pressure, our blood pressure. So this is when they actually measure your blood pressure, this is what we get. If you have 120 over 80, say is your blood pressure, the 120 number is the pressure when the heart contracts. This is called the systolic pressure. It's the pressure when the heart contracts. And the word systolic actually means contraction. And then the lower number is the pressure when the heart relaxes. So you have a high pressure when it contracts and a lower pressure when it relaxes. And this diastolic pressure, that's what it's called. Is when the heart relaxes. And diastolic means a drawing apart. Right, systolic pressure is when your heart's contracting. That's the bigger number on the top, the 120, and then or whatever it is. And then the diastolic pressure is when the heart relaxes, so you get a lower pressure. All right, so we have some applications of our various principles in the heart. First of all, Boyles Law. Remember, Boyles Law, it was part of our ideal gas law, said that PV is equal to some constant value. We talked about this in terms of the lungs, that if I make the volume bigger, the pressure decreases, and that occurs in the heart too. That the heart is just a muscle, and it makes it big, small, or big, small, big, small. It makes those chambers inside of the heart to get smaller. And so when the heart contracts, that means that the volume decreases, and therefore the pressure increases. And that comes about from Boyles Law, because if the volume goes down, that means that the pressure has to go up. That those two quantities, the pressure and the volume, as long as the temperature and the amount of fluid in there is remaining the same, the pressure and the volume will, the product of those will remain the same. Okay? It's a bit of a reach because actually the ideal gas law, that P equals nRT, only applies to gases, but this does apply to fluids in this case for the heart, the Boyles Law.
Is that because it's a closed system?
Yes, because it's a closed system.
But in the book, didn't it say it's really not technically a closed system?
It's technically not a closed system, right? That you do have some exchange of materials in the blood, but it's not that much that comes and goes, so it's okay to think of it as a closed system. All right, and Pascal's principle in the heart says that the heart applies, if you remember Pascal's principle, we sort of illustrated this with like a piston, and if we apply a force over a certain area, the pressure is equal to force over area, then that pressure, which we're applying, will be felt all the way throughout at every point. So we feel a pressure that's felt everywhere. And that's the principle behind hydraulic systems. If I apply a pressure over here, I'll get the same pressure over here. And then I can finagle the areas and get more or less force. Okay? If it's an open system? No, because on an open system, like, a container with a hole in it, if you push down, then the water or whatever's in here is just going to squirt out. So no, it has to be a closed system. In general, all the things that we're talking about are related to closed systems. All right, so Pascal's principle in the heart applies a pressure. At contraction. That increases the pressure throughout the body. All right, so try to find your pulse. You'll try to find your pulse. I didn't try to find it. I finished writing, but find your pulse. You get it? Steven, you got your pulse? Find your pulse. Every time you feel that, that's your heart contracting. And it's applying a pressure up here, and it's felt throughout the entire system. Wherever, on your neck, or on your thing, on your leg, or wherever you find your pulse. That's Pascal's principle. That pressure that is applied up here is felt all the way throughout the system. That's kind of cool. That you can feel your heart at any part of your body. Anywhere that you have the circulatory system, which is everywhere. All right. Let's try a few questions. Which of these is greater? I want you to know the difference between systolic and diastolic pressure. Sort of what they are, what their values are. All right, so a few more seconds, 28. We'll do the one on the right next. All right, look at y'all, that's right. Systolic pressure is the greater. That's when we contract. That's what systolic means. And diastolic means a drawing apart. That's when the heart gets bigger and that pressure drops. Do y'all like jokes about sausage? Do you? Do you like jokes about sausage? That's a question. Those jokes about sausage, they're the worst. Okay, according to the flow equation, what happens to the speed is area decreases. All right, let's stop at 33. 33. All right, good. A is right. Flow equation, A1V1 equals A2V2. Or really, the flow equation is Q is equal to A times V, and this is a constant value. But we call this the continuity equation. But regardless, they're related. The speed is the area decreases. That means that the speed increases. So A is the right answer. We didn't talk about this, but it was in the book, so let's do it. Which of these phenomena cause the distinct sound when measuring? No, we did talk about this. When measuring diastolic pressure. Talked about this a week or two ago. A week ago, I guess. All right. Let's stop at 27, 8. There we go. B is right. Hey, listen, have y'all ever tried to squeeze out all of the dish soap from like a dish soap bottle? You ever done that? Where you, like we have a little container, we have to squeeze our dish soap into it. Y'all ever done that? Yeah, and you squeeze, and it's sort of coming out normal, but then the bottle gets smaller and smaller, and at some point you have to do what to the bottle? You have to sort of push it open so it comes apart. And what do you get when that happens? You get a lot of air that comes into it. That doesn't happen in the heart. But still, the fluid inside it just sort of gets all jumbled up, right? And a similar thing happens in the heart, that you contract and it pushes the blood, but then when you pull it apart, it's like you get a lot of turbulence moving around inside of the heart. Kind of like in the dish soap bottle when you pull it apart. Y'all know what I'm talking about? Am I the only one? Just me and Annette? Do y'all not have dish soap at your houses?
I'm a little confused because I don't know. I guess I was thinking when they were talking about when you're measuring it, like with the stethoscope. With the diastolic is when you no longer hear the sound. So I was thinking.
Oh, I don't know about that.
Laminar flow.
No, the diastolic is when you get that funky sound, like a thwomp.
Oh, that's when it starts. That's when you start to measure systolic pressure. First hear the sound, and when you no longer is the diastolic. I could be wrong.
I'll have to look into that. But the answer is B. It is the turbulence. But you're questioning the diastolic part of that question, right?
Yeah.
Pretty sure it's right. I'll go back and look.
What is diastolic?
Diastolic what?
Yeah. See, that's what I was. Yeah, it's when you stop hearing it.
I'll look
So-
into it. All right. So for an IV, when you want to put in drugs intravenously, where should you insert the needle? Into the vein or the artery? And why? Again, not something that we've talked about. Your book did, but you should be able to reason it out from what we talked about. All right, let's stop at 27, 8. All right. All right, good. A is right. Why do you want to use the vein? What is the pressure in the vein? Is that high pressure or low pressure? Low pressure. And so when you're administering drugs, you want the pressure differential to be as big as possible, right? So that you have a high pressure in the IV bag and a low pressure into the vessel, or the vein in this case. So you have a vein which has a low pressure. And this increases the pressure differential. All right? I have this buddy, and it's terrible. It's a terrible situation for him because he's addicted to brake fluid. He just drinks brake fluid, like all day long. But he says that he can stop at any time. That was a joke. Like, I know that there might actually be people that have various addictions. I'm not sure they drink brake fluid, but yeah, I think it would probably kill you if you drank brake fluid. I had an uncle who was an alcoholic, and he was also really poor, my great uncle, and he would drink almost anything that he could get his hands on. It was really sad. He would drink like kitchen cleaner type stuff, just whatever you go into your house and just find whatever he could. All right. What happens to the speed of the blood as it moves from aorta to capillaries? Does it increase? Let's do this as a clicker. Increase, decrease, or stay the same? When it moves from the aorta to the capillaries, what happens to the speed? All right, let's stop at 25. Oh boy, we're all split up on this. It's going to be decreases. In fact, that was the figure that we showed in the book earlier, where it showed the capillaries. Well, what did it? What page was that on? On page 56, and it gives the area, or it gives the speed. The speed in the capillaries for blood is about 0.1 centimeters per second. But up here in the aorta, it's about 3 centimeters per second. So it goes a lot faster, right? 30 times as fast in the aorta. But the reason that that this happens, because we know that A1V1 is equal to A2V2. But this has to remain constant at all times, that the product of the area and the speed has to remain the same, is because the area of the aorta is relatively small. It's about 3 square centimeters, but the combined area of the capillaries, now the individual area is really small, but the combined area of the capillaries is 900 square centimeters. So if you look at the product of these, this is 30 centimeters per second here, sorry. If you look at the product of those, 30 times 3 is 90. 900 times 0.1 is also 90. So we still have the same flow rate through the aorta or the artery and the capillaries, but we just have a much decreased speed through the capillaries because the area is so much bigger. So with the capillaries, the area has gone up and the speed goes down. That's why the blood flows so much slower in the capillaries. That might not make sense. Let's just make sure that you're aware of what I'm saying. I'm not saying that the area of the capillaries is getting smaller. Individually they are. But combined, the combined cross-sectional area of the capillaries is a lot bigger than the other parts of the systemic circuit. Got clear what I said there? The area is bigger for the capillaries when you consider them all together. All right, a couple more. So as the blood flows through the aorta to the capillaries, the pressure differential drops, right? High pressure aorta, low pressure coming back into the vena cava. According to the Poiseuille equation, what happens to the flow rate? No, I don't like this question. Let's just skip it, okay?
The flow is supposed to stay the same.
Yeah. Yeah, let's skip this. I don't like these questions at all. Let's skip them. In fact, let's, I don't want to start in IV stuff right now. Oh. Let's just call it a day, okay? I'll see you on Thursday. That's in a couple weeks. We'll finish up this chapter, and then we're shooting for a reading quiz on Tuesday, okay? That'll be the next chapter, the physics portion of the next chapter. What's that, Steve?
Said I got a problem.
What's wrong? Where is it?
Either my sister has, but she grabbed mine by mistake, and so we're switched, or...
Sisters. If you can't find it, come see me. I might have an extra. Oh, what book? You mean this book?
No, not that.
Okay.
Not that one.
The workbook?
The workbook.
I think I might have an extra if you come see me. But look and see if you can find it.
Oh, yeah. I'm like 90% chances I can see on a test.